Hi everyone. So in today's video, we are going to discuss the topic of meter bridge. Now this topic, it is there both in your theory as well as in your practicals. Okay, so it is all the more important. So this is the device meter bridge. Now this meter bridge, it is also known by the name slide wire bridge. Slide wire bridge. Okay, so let us first understand why this name. Okay, see, meter bridge or bridge, this word bridge, it is called bridge because this device works on the principle of Wheatstone bridge principle. Okay, so this is the Wheatstone bridge. Wheatstone bridge, and we have learned about this Wheatstone bridge principle in the previous video. I'm going to discuss here. Now it is called bridge because it works on the principle of Wheatstone bridge. Okay. Now why the name meter? Now the name meter is because this device uses a 1 meter long wire. This pink color line that I have drawn here. So this is a 1 meter long wire. So because of that, it is called a meter. Okay, this term meter. So meter bridge is 1 meter long wire and it works on the principle of Wheatstone bridge principle. Okay. Now slide wire bridge, the name is because here we are going to slide a jockey. I'm going to say what is jockey, but a device is going to slide over this 1 meter long wire. So that slide wire, that term has come from that. Okay. Now we have learned about Wheatstone bridge. Okay, and we have seen that in a Wheatstone bridge, like if these two terminals, they are at same potential, B and D, they are at same potential, then no current will flow through the galvanometer and the galvanometer will show null deflection. So if the galvanometer shows null deflection, then we can write P by Q, it is equal to R by S. Okay, P by Q equal to R by S. So in this expression, we have four quantities, P, Q, R and S. P, Q and R and S are the four resistances. Okay, now among these four resistances, if three resistances are known, we can find the fourth quantity. Okay, so that is Wheatstone bridge principle. That is under balanced condition, that is when no current flows through the galvanometer, the resistances are in ratio as P by Q equal to R by S. Now this principle is going to be used in meter bridge. So in meter bridge, we are going to determine the unknown resistance. Okay, this is a device which is used for determination of unknown resistance. Okay, now here let us understand the construction of this device. We have understood the principle, working principle. Okay, we know why it is called meter bridge. Okay, so those things we have discussed now. Now next, let us discuss the construction of this device. Okay, so basically it has, see, these are copper strips. This is a copper strip, this is a copper strip. This arrangement, this entire arrangement, it is fixed on a wooden board. So this is a strip, copper strip or any metal strip will do, but it should have low resistance. So this metal strip, it is fixed on this, suppose this green board, here it represents a wooden board. So this metal strip will be fixed on the wooden board with the help of this screw. These are two screws. So similarly, this is another metal strip. So it is fixed on the board with the help of screw. Now this is a gap. Here there is a gap. This is another metal strip. So this is one screw, this is another screw, this is another screw. So this metal strip is fixed with these three screws. Okay. Now similarly again there is a gap. This is another metal strip and this is another metal strip. So here is a screw, there is a screw, this is fixed, this is also fixed. Now this is one metal strip, this is another metal strip. Here from this end to this end, this pink color line, this line represents a 1 meter long wire. 1 meter long wire. Okay. Now this is a 1 meter long wire. 1 meter long wire. Okay. Now this wire is usually of constant tin. This is one alloy or manganese. So these two materials are used for this wire in the meter bridge. Now why it is used? Why these two materials are used? Because these materials have very high resistivity. And low temperature coefficient of resistance. Low temperature coefficient of resistance. Okay, now we have learned about this property of constant tin and manganese, that this material alloy, constant tin and manganese have high resistivity and low temperature coefficient of resistance. That is why they are used for making this resistor wires. Okay, so the reason is high resistivity means their resistance is not going to change very easily. Okay, as temperature changes. And again, low temperature coefficient of resistance also implies that if there is a change in temperature, again the resistance is not going to be affected. Okay, why we don't want the resistance to change? Because here we are going to measure an unknown resistance. Okay, now here I told you that here there is a gap, two gaps. So in this gap, left gap, this is one resistor, and the right gap there is again one resistor. This is the known resistance. This is the known resistance and this is the unknown resistance. This is the unknown resistance. So using this device we are going to find this unknown resistance S. This is the known resistance R. Okay. Achha. Now we want to calculate this resistance. Okay. So the other resistances, see P, Q, R, as in Wheatstone bridge we have 4 resistances. Here also we have 4 resistances. I am going to show where are those resistances. Okay. So here, see, I told you P, Q, R and S. So suppose S is the unknown resistance. So this unknown, we can find this unknown quantity only when we know the other 3 quantities. Okay. So other 3 quantities must be a constant. Okay. Their values must be fixed. So it is for this reason the resistance of this wire should not change as we conduct the experiment. Okay, because as we conduct the experiment there will be flow of current in the wire. Now if the current flows continuously, temperature may rise. Now if the temperature rises, the resistance may change. We don't want that to happen. So because of that we use constant tin or manganese. Okay, manganese for this wire in the meter bridge, because they have high resistivity and low temperature coefficient of resistance. Okay, acha. Now, so here we have connected one known resistance. Here in this right gap between these two terminals, we are connecting one unknown resistance. Okay, acha. Now this is terminal A and this is terminal C. So between A and C, we are connecting a battery. This is a battery with a key. Okay, and this is suppose some terminal P. Okay, so from P there is a wire and this is connected to galvanometer. Now galvanometer will, so this is the galvanometer. So galvanometer will have 2 terminals. One terminal is connected to this side B, one terminal is connected to D. So here this is one terminal is connected to P, the other terminal it is connected to this arrow is a device called jockey. C-K-E-Y, jockey. Okay, jockey is like suppose this thing. Now this is a chalk holder, but a jockey it looks like this only. Here in jockey what will happen? There will be a screw here. There will be a screw, and from the screw inside this is a plastic body. So inside this body, suppose till this point, there will be a metallic rod. Okay, and this screw, from this galvanometer, this wire is connected to the screw. Okay, and from the screw you have a metal rod. This is the tip of the metal rod, and that tip can slide on this wire, Okay, acha. Now we will try to locate the point. We will make this slide. We will slide this jockey on this wire, this constant or magnetic wire, so that at some particular point the galvanometer shows null deflection. Suppose this happens at this particular location. So at this particular location, the galvanometer is showing null deflection. Okay. What we will see that there is, along with this wire, there is a scale, and this scale is a meter scale, 1 meter long scale. So along with the wire we have the scale, so we can know what is the length from this point to this point. Okay, now suppose that length is L. Now this is a 1 meter long wire. Okay, so that is 100 centimeter. So if this is L centimeter, this length is L centimeter, A to D. So D to C will be 100 minus L centimeter. Okay, acha. Now you will think that, okay, how we are going to find the unknown resistance? We are only observing the length. Here we have 4 resistances. So for that we need to understand how we have studied the Wheatstone bridge principle. See, if you should be able to see the Wheatstone bridge in this device. See, this Wheatstone bridge, it has resistance P, Q, R, S. So I can represent them as this is P, this is Q, and this is R, this is S, and this is galvanometer, and this is the battery. Okay, with the key. So with the key, this is the key. So I can redraw this Wheatstone bridge just like this, isn't it? This circuit and this circuit both are same. Okay, acha. Now if I replace this P and Q as R and S. So this is R, this is S. Okay, this is the galvanometer. This is R, this is S. Here we have the galvanometer. This resistance is RL, that is resistance of length L. Okay, and this resistance is resistance of 100 minus L, that is resistance of this part. Okay, I don't know the resistance, I know the length. Okay, acha. Now see, resistance, it is proportional to length, because resistance can be written as rho L by A. Resistance is rho L by A. Now from this end to this end, we are using material of same nature, wire of same material. So this rho, it is a constant. This wire is of uniform cross section area. So this area is also a constant. So I can say resistance is directly proportional to length. So if resistance is directly proportional to length, so that means resistance of this part, it is RL, it is proportional to length L, and resistance of this part, it is R 100 minus L is proportional to . So similarly for this segment, the resistance R 100 minus L, it is proportional to length 100 minus L, because length of this part, it is 100 minus L. So if these two quantities are proportional, we can very well divide them. So if we use Wheatstone bridge principle over here, so this is C, R by RL, it is equal to S by R 100 minus L. Correct? So that implies S is equal to R 100 minus L by RL into R. S equal to R times R 100 minus L divided by this quantity. Now, if you use this relation over here, what do you get? We get S is equal to 100 minus L by L into R. Correct? So, if you know this resistance, so if you know this length, L is known. So L is known means 100 minus L is known. R is the known resistance. So we can calculate the unknown resistance S. Okay. So this is how we can calculate the unknown resistance with this device called meter bridge. Okay. But the only thing is, see, sometimes errors might creep in. So to avoid that error, what we do that this balancing length, the point at which the galvanometer gives null deflection, it is adjusted near the middle point, near the midpoint of the meter bridge. Okay. Now how it is adjusted? By adjusting the known resistance. By adjusting the known resistance, we can obtain the balancing length near the central region. I am not saying that the this null deflection should be obtained exactly at 50 centimeter. Like it should be like in the range of 30 to 60 centimeter, in that range, near the central region. So by doing that, we can avoid various types of errors in this experiment. Okay, so to avoid error in the meter bridge experiment, the known resistance is adjusted so that the balancing point is obtained near the central region. Okay, so that is the one important precaution that you need to take while doing this experiment. Okay, so this is the working of meter bridge for determination of unknown resistance. So now, based on our understanding on the concept of meter bridge, let us solve this question. In a meter bridge, the null point is found at a distance of 40 centimeter from A. So this is A and A. So from A at a distance of 40 centimeter, the null point is found. With this known resistance, this is the known resistance and this is the unknown resistance. Okay. If a resistance of 12 ohm is connected in parallel with S, so in parallel with S, if a resistance of 12 ohm is connected, the null point occurs at 50 centimeter. So find R and S. Okay. So first part of the question, it says that the meter bridge, the null point is found at 40 centimeter. So this is 40 centimeter and this will be 100 minus 40. So R by S, it is equal to this resistance by this resistance is equal to this length by this length. So this length is 40 and this is 100 minus 40. 100 minus 40. So this is 40 by 60. So that is equal to 2 by 3. Okay. So this is one condition. Second condition is if a resistance of 12 ohm is connected in parallel with S. So this is S. So in parallel with this, a resistance of 12 ohm is connected. 12 ohm is connected. So now the balancing length is at, the null point is at 50 centimeter. Null point means balancing length. So if L is 50 centimeter, 100 minus L will also be 50 centimeter. So now this is R by, now this resistance is, these two resistances are in parallel. So that is 12S divided by 12 plus S. It is equal to, so this 12S divided by 12 plus S, that is the equivalent resistance of these two resistors in parallel. So this is equal to this length by this length. This length is how much? 50 centimeter. And so this is also 50 centimeter. So 50 by 50. So that is equal to 1. So that gives R, it is equal to 12S divided by 12 plus S. 12 plus S. Okay. Now from this, we have R, it is equal to 2s by 3. R equal to 2s by 3. So here this R can be replaced by 2s by 3. So this SS gets cancelled. So this is 2 6 times. So this is 12s so this is 12 plus S is equal to 18, or S is equal to 6 ohm. So we have to find the value of R and S. So S is 6 ohm. So that 6 ohm, if you substitute over here, so R is equal to 2 by 3 times 6. So this is R is equal to 4 ohm. So the value of R is 4 ohm. The value of S is 6 ohm. Okay. So this is how we can solve this question.